great to show up, including people who aren't even in the program anymore, I think. Are you taking classes?
No.
No? Okay, well, great to see you here. And Raquel is a candidate for a master's degree, and she'll be speaking today on application of Gaussian processes and maximum entry sampling in methane plume prediction.
Awesome. Well, thank you, and thank you for coming. So this is primarily a machine learning topic. So mostly we did our work with statistics, and then there's little highlights of information theory, but you'll see that as I go along. So then my thesis committee, Mark Schilling, Dr. David Thompson from JPL, and Dr. Killian. Okay, so diving right in, the motivation for this project, right now the ways of sampling methane include everything from walking around with a handheld sensor to slapping one on the back of a truck and driving around and only getting samples for those specific areas. So you can see this is a map where, I mean, if I had to guess, I don't actually know, it looks like they only have the methane samples on those specific roads, and then you can see the different values represented by those peaks. But they don't really have an accurate representation of what the plume looks like, where it's coming from, so on and so forth. So that is what we are trying to address.
Do you think those are factories?
Maybe. I should have looked up the details of the black vein. Okay, so our objectives to create an algorithm that interpolates the entire concentration field given a subsampling, and then create a sampling strategy that we can couple with that interpolation algorithm to optimize our information gain. So our suggested methods are the Gaussian process model, and then for sampling, maximum entropy sampling, and I will be explaining what these are. So just an outline of what I'm going to be talking about. So the interpolation method, I'm going to give you an introduction, kind of a reasoning for what we did, and then the background that you need to understand what a Gaussian process is, and then talk about some of the innovations that we made to this model, and then I'll show you some of the simulated results that we did, applying the different innovations, mixing and matching. And then I'll talk about our maximum entropy sampling technique, and I'll show you some of the simulated results that we got for that. Most exciting part is that we actually have one field experiment data that I can show you, and it's very, very cool, and it was sampled using an orthocopter. And then I'll talk about the future work that we did not get to address. So, like good, all good applied problems, we start with our assumptions. So we assume that every subset of spatial points in the field that we're considering, the probable methane values will take on a multivariate Gaussian distribution. So I'll go into what this means more. And then each methane value is finite. So we mostly do this just so we can restrict our class of random variables to the ones that have finite first moments and have a probability density. And then lastly, the covariance relationship between the methane values is a function of the input space. So I will explain to you what that means as well. So just to begin, if you imagine we have one point in our spatial field and we have a probable methane value that is connected with that point in the spatial field, we assume that that methane value takes on its values according to a Gaussian distribution. So it's most likely to be nearest the mean, with less probability of being out on the tail ends of the distribution. So similarly, if we have two spatial points, both of them individually still have a Gaussian distribution, but then they will affect each other. So if you think about, we have one spatial point that's 1 centimeter away from another, those are going to be very, very highly correlated. So that is reflected in our covariance function. Whereas if you have one point that's very, very far away from another, then we don't want it to be as correlated, and it'll be a decreasing function of the distance between them. So they affect each other, so we have a joint Gaussian distribution, and so we just keep on adding more and more points, so we can collect as many spatial points and have our probable methane values for it, and that will be our group of collected random variables. All right, so just a little bit of background before I go into the definition of a Gaussian process. So the multivariate Gaussian distribution, so if you have a random vector with a mean vector of mu and a covariance matrix of sigma, this is the probability density function. Hopefully everyone has seen that before. Something you may not have seen before, though, is the definition of a stochastic process. It's a collection of random variables where it's basically a function of the input space t, or the index set space t. So for our project, our index set is going to be the spatial coordinates in Rn. So that makes sense, hopefully, with what I've been saying. If you have a spatial point here, that's our input space, and the probable methane value will be that f of x, right? And that will represent our methane value at that point. So then our mean function for a stochastic process, you can see it's just the expected value of the stochastic process denoted in m of x, and the covariance function similarly is here. So hopefully everyone recognizes that as well as the general definition for the mean and covariance function of a random variable. It just so happens that our random variables are functions this time. All right, so what we've all been waiting for, the Gaussian process. It's a collection of random variables, any finite number of which are going to have a joint Gaussian distribution. So formally, we have a set with our index set being elements of Rn. And so we call it a Gaussian process if we can take a finite set in our index space, and then every random vector will have a multivariate Gaussian distribution. Okay, so just relating that back to what I've been saying, if we have an n-dimensional vector of random variables corresponding to our spatial points, that's an n-dimensional vector of random variables corresponding to the different methane values at those spatial points. Each one of those individually has a Gaussian distribution, and every subset of them from our spatial field will have a multivariate Gaussian distribution. Thus, it satisfies our definition of a Gaussian process. Okay, so we begin by defining the prior process. We want to make some assumptions about the underlying function and then include the training data set that we have. So we're going to use Bayesian statistics. Hopefully everyone is somewhat familiar with that as well. So, so instead of having a prior distribution, we have a prior process this time. So we have our training data set. We have xi and yi. Y will be the values that we have observed. And then the f of xi is the random variable that corresponds with that observed value. So remember, just going back to our goal, we wish to make output predictions for the random variable f of x star, is how I denoted it, for all new inputs x star. Everyone still with me? Okay. So a Gaussian process is completely parametrized by a choice of mean and covariance functions. And then just a little bit of notation, we can say that the function has a distribution as a Gaussian process with mean function and covariance function, as you can see there. So we assume that the prior mean function is just the zero function. This is done mostly for notational simplicity. It makes our lives much, much easier. Next, we define the prior covariance function. This is something else that hopefully my 440A people are familiar with. So we assume that we have the covariance function as a squared exponential. So as you can see, as I assumed in the beginning, we have a decreasing function of distance. Hopefully everyone's familiar with that. But notice right now that we cannot change the distance that it takes to not see a correlation between values anymore. It's very set. There's nothing that we can do to tailor this to the data that we've seen. So we add in one refinement. This is the hyperparameter length scale. So you can see we have the addition of it. The function is exactly the same, except we have this length scale term on the bottom. So this allows us to change how short the distance needs to be for the values to not be correlated anymore, or how long it needs to be. So let me just show you. So we have a 1D example. These little stars are, not stars, crosses, are observed data points. And you can see with the length scale 1, it's smooth enough that there's not enough variation, but it still allows the function to go through all the observed data points, as opposed to length scale of 0.3. There's way too much variation in between, and it still goes through all the points, but it's kind of uncertain, whereas length scale equal to 3 is an over smoothing. It doesn't go through all of the points at all. Okay. So then we say that our covariance matrix is defined by that covariance function. So the ij element of the covariance matrix is defined here. So then note again that since our covariance function specifies the elements of the covariance matrix, any subset of our input space will have a joint Gaussian distribution. So our entire input space will have will be Gaussian process. Okay, so throwing another hyperparameter at you that allows us to tailor our covariance function even more to the observed data that we have, we assume that our observations are noisy. So for each place that our input vectors, so where I is equal to j, we have this noise variance term that gets added to our covariance. So you can think of that as if you sample at the same place in the spatial field twice, there's going to be some variance in the values that you see, and that's modeled by this noise variance term. Okay, so here we have the joint distribution of our observed data y and the function values of the unobserved locations. So this embodies everything that we have assumed about the data thus far. What we really want to do is incorporate the training data that we've seen. So again, we're going to use Bayes' rule, where we incorporate the likelihood of the data, the prior that we just defined, and the marginal likelihood. So I'm going to give an example with two data points. So here, we have a prior. It has what looks like a mean of 0. This is out 2 standard deviations. So at every point in this input space, say we just pick one, say we pick 0.5, all the possible output values, so the f of that x, if we take a sample of n possible output values, those are the things that are going to be distributed, have a Gaussian distribution. So at each of these different inputs, the possible samples of the functions will have a Gaussian distribution, and then all of them together have a joint Gaussian distribution.
So each of the curves on the left is a realization of the prior. It's a sample
There we go.
taken from the prior, right?
Thank you. Yes. So then here we have 2 observed data points. You can see that the variability is minimized around them, and then the farther you get away from them, the variability goes out again. So that's what we're going to be doing. All right, so don't let this scare you. So what we want to figure out or find is the probability distribution of the unobserved data given the observed data at those locations and the locations of the unobserved data. Pretty simple. So we do that using the likelihood function, which again, my Math 440A people should know what that is. So that's just the likelihood of getting those observed values at those locations, given the unobserved locations and the unobserved values. And so that's just the product of the probability. Hopefully everyone remembers that. And then the marginal likelihood is the probability of getting those observations given the locations again. Okay, so this results in the predictive function here. So again, it's the distribution of our unobserved data, given our observed data, their locations, and the locations of the unobserved data. So that just shows you kind of our process of how we are deriving these things. You don't need to understand that, and the full derivation of those are in my paper. If you are interested, I can send you a copy. Okay, so that is our first step in incorporating the data that we have observed. So our next step is we want to optimize our hyperparameters. So I'm going to throw one more at you. I'm adding in this signal variance. It's right here. So that'll scale how much the values can differ from the mean that we have seen. So before I showed you an analysis of the length scales, where you just kind of pick one and then see how it affects our graphs, we could do, some sort of brute force when we pick different hyperparameters and see how they work. But really what we want to do is optimize them according to the marginal likelihood. So this is something that, again, I think my math 440 people have seen.
Might be giving them too much credit.
You covered a lot. Okay, so we maximize the marginal likelihood. And if you think about what the marginal likelihood is, that makes a lot of sense. So the marginal likelihood is the probability of observing those values at those locations, right? So if we maximize that in terms of the hyperparameters, we really all fit. So the marginal likelihood is equivalent to maximizing this equation. So you just take the log and it looks slightly prettier as far as taking partial derivatives. So then we will solve this wonderful system of equations. So it's a little bit ugly, but it's still doable. Notice here that there is an inversion of a n by n matrix, and we actually use some numerical analysis techniques for that one, but still doable. Okay, so now that we have the basics of how to incorporate the data that we have observed, I'm going to talk about the innovations that we have made to this process. So again, going back to the length scale, the addition of that length scale allows us to tailor, how far or how close you need to be for your values, your methane values to differ significantly. But right now, the problem is that it is spherically symmetrical, which isn't necessarily realistic for a methane plume. So if you think about a methane plume, let's say it's shooting off in this direction, the samples that you take along that plume, those values are going to be very, very highly correlated. However, if it's going off in this direction, the samples that you take perpendicular to it, I guess, will not be as highly correlated. So it doesn't make sense to have the same length scale in both of those directions. So we add in, length scales for each direction. So, but it isn't necessarily true that our plume is always going to align with an axis. So what we do is we rotate the data in our algorithm so that the wind is aligned with an axis. And then when we do that minimization or maximization of the hyperparameters, the smoothing along the wind axis will be shown, and the less smoothing in the other direction will be shown as well. And that's called automatic relevance detection.
So in practice, before you fly the orthocopter, you would actually take a wind reading, I guess, of the prevailing wind, and then...
Yeah, so when we went out into the field, we found a bag and hung it up on a thing and decided which way we thought the wind was going. Okay, so our next innovation is, if you think about the methane values that we're going to get, we can't have negative methane values. So actually our distribution of possible values is going to look more right skewed than it is as a bell curve. But if we take the log of the data, which is actually a relatively common technique in statistics as well, I think it's normally called the log transformation. You've probably heard of that also. Then our data will look more like a bell curve. So it amplifies the difference between our smaller values and dampens the difference between our higher values. So it's more reasonable to assume that the log of our data will be distributed as a Gaussian process. So here's our definition of a log Gaussian process. What it really is just taking, like I said, the log of the data and then assuming that that is distributed according to a Gaussian process. All right, so now we get to move on to the fun part. So we did some simulations. Here is a picture of a simulated methane plume. So what we did is take a gridded sample from this methane plume, so every 50th pixel through grid, we took those as our sample values. So the pixel locations was our input space, and the pixel values signified what we thought was our methane values. Everyone with me on that one also? Okay, so then we fed it into our algorithm, here is the interpolated methane plume for the regular Gaussian process. You can see that it interpolates it rather accurately, but then at the log, again, you see the peaks in the values a little better for the log. With the wind axis, you can see that that length scale is really affecting the smoothing in the direction that the wind is going, and then there's less in the direction that the wind is not going. And then the combination of the wind and the log, we see the higher values being, or the peaks in the methane values are interpolated better. And then again, we have that smoothing in the direction. So then we also did a test that had a finer spaced grid. So I said we took every 50th pixel value. Well, these are taking every 75th pixel value. So you can see for the regular Gaussian process, it couldn't even interpolate what it thought the plume looked like. However, when we took the log Gaussian process, it was able to find it. Again, with the wind, you see a lot of smoothing, maybe a little bit too much. And then with the wind log, again, we have that peak in the methane value and smoothing in the wind direction again. So for a little bit more tangible analysis of these images, I took the residual sum of squares of the interpolated pixel values versus the pixel values. You can see that the wind and the wind log kind of rival each other to search for which one has the best residual sum of squares. Hi, thank you for coming. Okay, so now that we have a way to visualize and interpolate the methane plume, we want to introduce our sampling method. So this is maximum entry sampling. So for those of you who are semi-familiar with information theory, I'm sure you've seen this definition before. This is the definition for the amount of information for a continuous random variable. And then the definition for the entropy is just the negative of that information. So basically 2 different ways to think about the same thing. So I'm not going to show you the derivations, but for a Gaussian random variable, we find that the entropy is equal to this here. So it's just an increasing function of sigma squared. And then similarly, with for the log Gaussian distribution, we have the same thing again, but we have this addition of the mean term. So considering just this one, so we can think of, so sigma is our variance, right? So sampling at places that have the maximum entropy are going to be sampling at places that have the maximum variance. So, but since our variance is a decreasing function of distance, we're going to end up sampling in kind of an evenly spaced grid until we've sampled pretty similarly all around the field, regardless of what we are interpolating our plume to be. But if we use the log Gaussian process, this mean term, so this mean is what we are interpolating our methane values to be. So places where we have found a peak in the methane values are going to cause more sampling in that area, because that'll make our entropy higher, because our mu will be higher, and so it's going to sample around that plume some more. So let me show you what I mean from our simulations. So here is another simulated methane plume that I used, just taking pixel values as our methane values. So beginning with just the regular Gaussian process, it randomly selected a spot to start. So here it started here. It selected the place with the next closest place with the highest entropy, which is this green dot, and it goes there sampling the entire way, and then it repeats the process. So then it decides that this next green dot is the next closest place with the highest entropy and samples all the way to there, and so on and so forth. And I cut it off after, I can't remember how many iterations, I want to say maybe 300 or so. So then,
if you really, the methane plume didn't really have much to do with it, but the correlation was important. You would want to sample like this and be really going out to the edges so you get the points all away from each other.
right. But then you can see, so it does sample relatively okay the entire field, and it does run into this methane plume, but we don't get enough information about it to interpolate what it looks like correctly. So this is what it assumes that the methane plume looks like, which isn't quite accurate.
Again, in the first picture, just to make sure I understand, it seems like it's heading towards the plume as time goes on, as you continue to sample. The additional sample points are heading over there to the other side. Is that?
It doesn't have anything to do with the plume being there, though. It's just because we started here, and then the entropy is just a function of the variance, and the variance is decreasing as distance goes on. So this is farther and farther away from what we know now. So it doesn't have anything to do with the plume. However,